Hey everyone, today we're going to talk about some assembly theory. So this should be exciting. We're not actually going to do any coding in this video. We're going to just talk about why things work the way they do and show you a little bit of what's going on under the hood. Now, a lot of other people will cover this right away. They'll talk about what registers are, the stack, how to use them, everything that's going on before you ever write a single line of code. And I do not personally like that approach. I like the give me code, give me something that works, something that I can actually use, and then later on I'll circle back and I'll find out why it works. And maybe I won't. Maybe I will not circle back. It all depends on how useful it is to me. Um, I want to learn how to drive a car and take it places and go get food so that I can eat and live. I don't necessarily care to know why that car works right away, but then later on, after the fact, if I start to have car issues or something, I might go, oh, I really should know more about engines and accelerators and pumps and different things so that I can maintain my engine and make my car last longer. So I don't necessarily care at the get go all that information because at this point the car is not useful to me. Well, I have the same approach with programming. I want to be able to do something and I want it to work. And then later on I'll come back and find out why it works and maybe I'll write my code more efficiently going forward. So, back to the topic on hand. What are registers? Well, let's imagine that there's a building full of lockers. We'll call this a locker room. And in the locker room, you can store anything you want. And let's say you throw something in locker 101 and locker 302, maybe even locker 765. It's a really big locker room. You can put things wherever you want. This is the equivalent of RAM, random access memory. This is the active memory on your computer. You can store things anywhere you want in there, and you can come back and you can access that information or that item. Well, let's imagine that the playing field for whatever sport you're doing, it's going to be outside, and let's say it's a good quarter mile away from where your locker room is. And it just so happens that right at the field they have little lockers for the players to use. Now, when you want to store something long term, like let's say you play multiple sports and one of them requires a helmet, and this sport you're playing now does not require a helmet, you're going to keep it in the main locker. You don't need it. It's a hike to get it, but you don't care. You're not going to be running that quarter mile back and forth to go get it constantly. But let's say something like your wallet. Let's say you don't want to keep that necessarily in the locker room, and you don't want to keep it on you while you're running around on the field. You need to keep it someplace that's nearby, and maybe because they have like a lemonade stand or something there, you want to buy a lemonade during your break in between halves or quarters or however this fictitious game that we're talking about is played. And you want to be able to buy something to drink, but you don't necessarily want to have to run a quarter mile to get your wallet and then run a quarter mile back, buy the item you want, and then do the same thing again. You want to keep it close by. Well, that's basically what a register is. It's these fictitious lockers that we have that are right by the field. And another analogy you could use, though, too, is in the locker room, you probably own that specific locker. Like if you have a gym membership or whatever it is, that's your locker. You put things in there and you take things out, and if you have a lot of gear for some reason, you might have more than one locker. Well, the lockers at the field, though, are something that I'm sure there'd be a sign on it that says, please do not leave items in lockers overnight, because every day when whatever game this is that's played, people are going to want to keep things nearby. So these are lockers that are used all the time, used by different people, very temporarily, and they're very quick to get to. This basically summarizes what a register is. A register is uh, a type of memory. I'm hesitant to use the word memory because that that means something. Generally, it means like random access memory and uh, whatever. It's a type of memory. We'll say that inside the processor itself. So it's really close, really fast, easy to get to. Basically takes zero time to get to it. All right, and it's also like a global variable. So, like I said, anybody can get into these lockers. Seems kind of concerning that your wallet might be in there. So we'll say any of the players, hopefully the people you're playing along with are your friends and they're not going to steal your wallet on you. But they're very easy to access and things might get swapped in and out all the time. Using a programming example, since this is programming, let's say you have a global number and we're going to use like a C style example in here. And let's say you want to increment that global number. So you have increment, and it just takes your global number plus plus, and then let's have a decrement as well. That might just be spelled decrement, is it? Let's check Google on my other screen here. Google doesn't even know what I'm looking for. All right, I'm just going to say I'm right, whatever. Minus, minus. All right. These two functions don't really know that each other exists. That when they're called, they modify this global value. If you add another one that says use value, it can do anything it wants. It could say, I want to use it somehow, and then I'm going to just subtract from it because I've used it. And these are none the wiser that that happened. And this is why you normally don't program with global variables, because they can be a nightmare to remember what is going on unless you're keeping really good track. Well, you get to keep really good track when you work with assembly. These things are rewritten so often that I would say every 2 to maybe every 3 commands that you run, they're probably going to start changing. Like your flags, we'll get to that later. Those will be changing all the time on you. So anyway, though, it's like a global variable. Next, let's talk about the stack briefly. So if you've ever gone to one of those buffet restaurants, and if you're not from America, you might be wondering what on earth I'm talking about. It's one of these places where you pay like, well, now they're probably like $15 to get in the door, but once you go there, it's all you can possibly eat, and they have every type of food you can imagine under the sun, and a lot of the foods don't go well together. I still don't exactly understand that, but you figure out what you like, and you go and you get a plate and a fork and a spoon or a knife or whatever, and then you fill your plate up and go and you eat, and then you leave your plate behind and go get another plate, and you eat until you can't possibly eat anymore because you paid money, a lot of money, to get in the door. So you're going to get your money's worth, which is probably the reason these places usually shut down, because everybody has that mentality. Anyway, though, they have a stack of plates there. And let's imagine that the plates are different colors, and all their plates are white except for one. There's a blue one, and that it happens to be the plate that you want. Let's say the kitchen comes out and they had just washed 5 white plates, and the blue plate was on top, but before you got there, the kitchen crew came out and they put those 5 plates on top of the blue one, and the blue one went down into the little chamber where it's hidden away. To get to your blue plate, you need to remove those 5 plates off the top of the stack. It's a stack of plates. Moral of the story is, the first information that goes into the stack is the last information that comes out of the stack. And it's a very organized system of memory where the data is kept. This is what C uses with your local variables and things like that. There's stack frames, all sorts of stuff. Rather than going out and trying to find a spot in memory and say, I'm going to use this for a very short period of time, not as short as a register, but still a very short period of time, rather than going to, if we use our locker analogy again, mixing metaphors is always good, but rather than going to whoever owns the locker room and saying, hey, I need 4 different lockers, and you get 4 completely different numbers, and then you got to remember what's where and keep track of it and write yourself notes in the form of pointers. You can just say, I need a bank of 12 lockers, and I will just fill them up one by one, and then when they're full, I might fill it up halfway, and then I'll take a few of them out, and then I'll fill in some more, and it's first in, last out, like I said. All right, so that's more detail than you probably wanted to know. Let's get into the registers themselves. If you've been looking at the code, you've seen AX, BX, CX, DX, SI, DI. You're probably wondering, how many of these things are there? Does it just keep going and going? And well, on 30-bit processors, it actually does. There are more. But in 16-bit real mode, which is what we're mainly talking about, what you see on the screen is what you have to work with. These are all multi-purpose registers, which means that they can pretty much be used for anything. Now, obviously, if you're calling an interrupt, it will say in AH, I'm expecting this, and then I'm going to modify AL. So then you need to obviously use AH and AL. All of these will have an H and an L in them. So there's AH and AL, BH and BL, CH and CL, DH and DL. What does that mean? Well, in AX, you can hold an entire word, which is 2 bytes. AH, which stands for the high byte, is only 1 byte. And AL is also only 1 byte. Having a typing crisis here. All right. So you have the high end and the low end bytes. And that basically sums it up. You can either set only 1 byte or you can set both of them. If you know you want to set AH and AL with an immediate value, then you probably want to just set AX right off of the bat, because it will be 1 less byte in your program for keeping track of things. And this is assembly. Why would we? We're here to save as many bytes as we can and run as fast as possible. So you would want to do AX directly. But if you're pulling from a memory location for 1 byte and immediate for another or something, then you'll probably break them apart. Next, let's get into string indexes. So this is going to be your source index, and this will be your destination index. And if you remember from our string operations, when we wanted to show text on the screen, we use our source index. And then when we wanted to save a user's value as a string into memory, we use the destination index. There you go. They hold addresses and they work with strings. Next, we have our stack pointers, or indexes, I guess technically they are. This one is your base index, or base pointer. I'm going to call them pointers because, I mean, there's a P in there. It's not an I. And then you have your actual stack pointer. The base pointer points to the start address. The stack pointer increments and points to the top of the stack. So if we use the locker analogy, if locker 100 is the beginning, that's where our base pointer's basically at. And then the stack pointer, let's say we put in 6 items, it'll point to 106. That's that. When you get into C and things like that, it's more intricate. These things will bounce around and move around, and it will actually save memories to keep track of things so that when it wants to free things, it can free a whole bunch all at once instead of having to do subtraction and things, optimization, blah, 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 blah. This is their purpose, though. After that, we have our instruction pointer, which is also called the program counter. Obviously, while a program is running, it needs to know which command to run next. Each of the commands are stored at a memory address in order of operation, and the program counter will just slowly increment through those addresses one by one, running your program, unless it hits a jump. In that case, it will jump to whatever address you told it to jump to, and then it'll start executing commands at that location. Pretty nifty. And these guys are segment. I want to say pointers. Let me see if my well, I guess segment registers is their normal name, so we'll go with that. Oops, what did I do? Registers. All right. So, what is segmentation? Let's do that before we get into these guys. Segmentation has to do with the ability to access more than just 16 bits of memory. If you recall, when we were looking at this, we said that well, any of these are able to hold a word or 16 bits. So if you only were able to access this much memory, you would be limited to a fairly small amount, I would say. I believe it's 64 kilobytes and less. And if your computer only had 64 kilobytes, then that would be kind of sad. So what they did is they figured out a way to add another nibble to that. And what they did is it's called segmentation. So in your segment register, you might have something like and you're probably looking at this and going, well, how does this help us? You said there's only a nibble. Well, the way it works is actually like this. So it will add, and its final result is it will go to address this address, which gives you a lot more space. And if I'm trying to remember correctly, I believe it's 1 megabyte that it'll give you. But don't quote me on that, because I should have looked that up, and I forgot to do that. And I'm not going to stop recording at this point. So just trust me, and if I'm wrong, I'm sorry. The weird thing about segments, though, is these are not always zeros. These can also be set to various things. This would cause an overflow, so I'm going to do it this way. I'm cheating. But look at that. The math still works out. The thing about segments is they can overlap because of this functionality. The fact that they can have these mixed values along the way as well. So that's just something to keep in mind. All right, well, enough about that. What are they? So this is called the code segment. Interesting. This is where your code is held, believe it or not. This is your data segment. I bet you can guess what goes there. All your variables. This is your extra segment. If you we haven't covered that yet. We will. We will eventually get into writing characters on the screen by directly manipulating the video's memory, or where the video has its memory laid out, and that will use the extra segment when we get to that. And then you have your stack segment. This is where the stack is hanging out. So there we go. We have all of our segments. There is one more register, and you can't actually write to it, and you can't actually read the entire thing either. It uses its bits like little checkboxes. They're called flags. And you'll have things like your overflow flag, your direction flag, your interrupt flag. You remember our little buddy CLI, clear interrupts? That's setting this one to 0. Then we also have the one that I never use, the trap flag. This is for stepping through your code while you're debugging, or debuggers can use it. Anyway, then we have our sign flag. We have our 0 flag. We've used this guy a lot. Remember JZ, jump if 0. That's I use that specifically so that you would understand that we're using the 0 flag, or there's also JNZ, jump not 0. Haven't used that as much. When I talk about comparing, which is basically how you do if-then statements for all sakes and purposes, we'll actually jump to another form where you have jumps equal and jump not equal, and that will, these are synonymous, JZ and JE, JNZ, JNE, and you might be thinking, well, why did the creators go through all this time to make things that do exactly the same thing? And we'll get into that because there's other cool things that we can do as well. Then you have your half carry flag, and you have your carry flag. So how are flags used? Let's say you do an add operation, and you're adding AX and you're adding BX together. In that process, we talked a little bit about the way our, I'm going to change this. I'm going to do AH and BH because I don't want to have to write out 16 little bits. We're just going to do 1 byte instead. So let's say that there we go. This is easy enough math. So 0 and 0 gives us 0, 1, 1, 0, 0, 1, and then 1 and 1 give us a 0, but it carries a number into the most significant bit. And this becomes where this is the most significant bit. This is the least significant on the right-hand side, and this is the most significant. And you might be wondering, well, why did they name it that? If I were to tell you I have a 1 and 6 zeros, and you can arrange that into your bank account in any order. So you could do 0, 0, 0, 0, 0, 0, 1, or 1, 0, 0, 0, 0, 0, 0, 0. Or you can put the 1 somewhere in the middle. The 1 at the very beginning would give you $1 million, and that'd be very significant. If you put the 1 way, way, way on the other side, way on the right-hand side, and put 6 zeros in front of it, you would have $1, which is very insignificant. That's the least significant decimal place or numerical place in the decimal system that you can use. Is way on the right, and way on the left is the most significant. Works the same way with binary. So when the most significant bit has a 1 put into it, when originally it was would have been a 0, that's called a carry. Just like you remember doing math, and if you have this number and you're adding this number to it, and you take 7 plus 5 and you get 12, so you write down to carry the 1. Yeah. Yeah, you were paying attention in elementary school. Carry the 1. That carry is what the carry flag indicates. Now let's talk about half carry. Half carry is if you carry over to this spot in this nibble, because you might be only working with 4 bits. Are you going to use that? You're probably never going to use that again in your life. And you might wonder, why does it start with an A instead of an H? Well, it's also called the auxiliary carry flag. So auxiliary starts with A. Why does it exist? Well, back when these processors were done, if you think about it, there's 8-bit processors, there's 16-bit, there's even 4-bit processors. Every bit at this point kind of counts. Now these days we work with larger numbers, and I'm just going to say you're probably not going to deal with it a whole lot. So we've talked about this. We've talked about this. If you do an adding operation and the final result is all zeros, like that, the 0 flag will be set. All right, we've talked about that. We are flying through these now. All right, the signed flag. So let me go back. One more thing. Just thought of it. The carry flag is also the borrow flag. So you remember how if we had to carry the 1 into the most significant bit, it would set the flag. If we started with a 1 in here and we did subtraction and we had to borrow from it, same concept with subtraction in elementary school, it will also get set. Just to mention that so that you're not wondering, well, why, what happens if you do subtraction instead of addition. All right, and let's see here. Let me look at my notes. All right. So we talked about if we carry 1 into here. If this is changed to a 1, and you might be thinking, well, obviously it would be. Let's say that this is the case, though. This is the number that we had here. And 1 plus 1 gives us a 0, and then we carry a 1, carry flag gets set. However, when you add 1, 1, and 1 together, you're going to end up putting a 1 here in the most significant bit, and then you're going to put another 1. Well, it goes nowhere. It overflows. So that is when that one gets set. It is an overflow situation. So if these two at the end up going out in the middle of nowhere, the overflow flag is set, which basically tells you that you overflowed your capability of storing information in this byte. All right, now you notice I skipped the sign flag, and the reason I did that is I wanted to make sure that the carry flag and the sign flag weren't confused, because when 1 and 1 come together, it carries into the most significant bit. However, whatever the final result of the most significant bit is, that will set your signed flag. So in this case, 1 and 1 come together, make a 0, and carry a 1. Carry flag would be set to 1. 1, 1, and 1 also would give us a 1 here, and carry, well, the overflow, we'll say. This final number here has a 1 in the most significant bit. That means the sign flag will be set. Now, if we had this, 1 and 1, we'd still have a carry, but now 1 and 1 are carried 1, and this one would give us a 0 and overflow our carry per se. The signed bit in this case would be 0. Now you might be wondering, why is it called the signed flag, and why what does signed mean? So there is a thing in computers called 2's complement, and it's really nifty. And as a matter of fact, it gives you the ability to have negative numbers. So when you're working with C or C++ or anything like that, you might remember seeing int, and then sometimes you'd see unsigned int, and you could always hold more values in the unsigned int but not negative numbers, and in the int you could store negative numbers. That's where this comes into play now. So if you have, we're going to get rid of this so it's not confusing. Let's say you have this number. This is obviously the number 0. If we do this, we get the number 1. Now, how does this signed bit mean anything? Well, it means negative. If you were to have this right here, this would give you negative 1. This is negative 2, and so on and so forth, as you basically count down from the most that you can possibly have. Now you might be thinking, well, how does this make any sense? Well, let's do a little bit of binary math. Let's go back to negative 1. If we add 0 and negative 1 together, we would get negative 1. This still makes sense. Well, let's say we want to take positive 1 and negative 1 and add them together. What do we get? Well, let's start over here. 1 plus 1 gives us a 0. We carry a 1. 1 plus 1 gives us a 0. We carry another 1. And it's going to be, obviously, repeat, repeat, repeat. When we're done, we're going to end up with a 1 over here, and the rest of this will all be zeros. Well, we can't store this, so actually this will trigger the overflow flag for us. We talked about that, but that means that our byte holds all zeros. So this was a nifty way that mathematicians figured out how to store negative numbers and still make math work in such a way that when you add a negative number and a positive number together, the math works out. All right, excuse me. So there we go. We have the signed flag. All right, next, the trap flag. This is used primarily by debuggers for debugging. We will not get into that. Done. Interrupt flag. All right, if this is set to 1, that means that the interrupt pin on the computer processor itself, if it receives a signal, that it will stop what it's doing and immediately do whatever that signal means that it should do. Like if you press a key on an old keyboard, it will actually interrupt the processor. When that's set to 0, like when we do clear interrupt, and then we call halt, the reason we do that is, I guess primarily if somebody is sneaky enough that while the program is ending, if all of a sudden you hit a key on the keyboard, it might go and run some sort of part of the program, and all your variables in theory are cleared out at that point, and they'll wreak havoc and destroy. Well, they'll get a blue screen of death error, I guess, basically. Yeah, that's what the interrupt flag does. It allows you to interrupt the processor. And then the direction flag, this is used for the primarily when you're working with strings and things like that. So, you know, when we were saving data into our variable, they would enter in letters and numbers or whatever as a string, and we would save it into a variable, and it would go from the left to the right with the number. Well, if you reverse this flag, it will go right to left. So basically you can save values backwards in strings. And if that sounds confusing, it still is a little confusing to me. But if you're a super experienced assembly programmer, you're probably going to say, oh, it's so handy because of dot, 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 dot. And it's over my pay grade. Actually, I don't get paid to write assembly, so it's way over my pay grade. All right, so I hope you found this educational. We got into theory, which isn't always the most exciting thing in the world, but we did talk about the different registers that you have access to. We talked about what registers were, how they're broken apart, their different specific purposes. We even talked about segmentation in the memory and how you're able to access more addresses than what you normally would think is possible. We talked about how flags are used and what each flag does. We will get into if statements per se. They're not really if statements, they're comparisons, but we'll get into that very soon as well, if not even maybe the next video. And we'll actually be using these flags, as you've seen examples when we do jump 0, jump not 0. We'll be doing more of that, and we'll be using more of these flags. So look forward to seeing you in that video. This video obviously was optional. You can completely skip the theory. And if you waited to hear that till now, I'm sorry. I could have said that up front, but I didn't. Didn't think of it till now. But really, I guess all these videos are optional. I'm not holding a gun to your head saying you must watch all of my assembly videos. So, whatever that's worth. I hope you enjoyed this though, and we look forward to seeing you in the next video.